There we go. So just continuing on the following up. So indeed, in robotics, there are many uses for deep learning, especially on the perception side. It's solving a lot of problems. And on the acting side, it's very difficult. One of the biggest problems, people think that if they can train the network to play chess, which is on the acting side and the planning side, and if they can do cats and dogs, then now we combine, so which is the perception side, then we can now do both. The problem is the number of examples that it takes to train these things. And if you're working in a lab and the robot takes 30 minutes to go from one place to another, because that's what the time it takes, generating enough examples there is a huge problem. People seem to do it very well. Robots, or at least the deep network models that we have now, don't do this well. So it's very much an open issue, and therefore, this is one of my arguments as to why the revolution in deep learning is affecting robotics less than we think. Now, this is just following up, and let me start actually by introducing myself. So my name is Gal Kaminka. I'm from Bar-Ilan University, and I do robots. And I noticed while we were doing this, while listening to the talks, that in fact, we're seeing two trends. Most of the people here from computer science are thinking about computer science, and this is a play on word in Hebrew, so the English audience will forgive me because the play will not translate well, but I will explain it. You can think of computer science, מדעי המחשב, as מדעי החישוב, the science of calculation. Okay? But you can also think of computer science as the מדעי המחשב, מדעי המחשבה, the science of thought or thinking. Okay? Now, if you notice, the people who are talking about AI belong to the latter category. So they're talking about a specific model, perception and action, actually, and you will see it very clearly also in my own talk. And you see, and this is a common theme that runs through it. It's a very abstract division of the work that's being done in AI, but it is there, and it's persistently there in almost everything that we do. With learning, of course, cutting through all of this. Okay, again, like search and like many other processes, you can apply learning, you can apply search, you can apply even planning, both on the perception and modeling side and also on the action selection side. But here you will find things like machine vision and sensor fusion, and on the other side you'll find planning and plan execution and goal deliberation and reacting and so forth. Now, my own personal problem that I'm married to, and I don't mean, of course, this is some sort of a joke, I am married to this problem, the nature of the social mind. Alan Newell, who co-founded the field of AI, used to say that you don't choose the scientific problem. The scientific problem chooses you. I was chosen for this work earlier on. First day I arrived at PhD school, for my PhD program, I met accidentally with Milan Tambe, who was my advisor. He was actually asked by who was going to be my advisor to talk to me about, because he was out of town. So he talked about his own work, and I fell in love, and I've been pursuing that ever since. I'm interested in what makes a single mind become part of a many. So what are the mechanisms that make a single mind part of a society? Okay? And this is very different than thinking about inanimate objects. And if you look at this very abstract architecture for how we build minds, you'll find that the issues translate very well. We have, on the perception and word modeling side, we're thinking about other minds. What do they mean? What do they intend? What did they did in the past? Can I predict what they're doing, what they're going to do next? So intents and plans, and in AI, this is generally plan recognition or goal recognition. And on the action and selection side, we're seeing coordination. So teamwork, and how do I manipulate others? How do I cause others to do something for me? How do I respond to the requests or the manipulations of others? And in this talk, I'm going to focus about robots that coordinate. So even though my interest is in the abstract notion of all these things, and of course in their computational implementations, for the purposes of this talk, I'm just going to focus on robots. And so there's a lingering question, which is completely different from everything I've talked about, which is why even talk about robots in computer science. And the reason I insist as a computer scientist to do robotics is because they keep me honest about where the problems are, where the actual computational limits are, where they actually hurts us. They give us, they tear apart the assumptions that do not hold, and they point the way towards solutions, in particular because we're combining not just the computation, but also the embodiment of those computations. And I think this is very important to say, and it was something that also Tali reflected on when he was talking about pushing some of the computation, in fact, to the dynamics of the environment or the body. And this is happening. Now, there is another reason where many people do robotics, And I like doing that for the same reason, which is just for the pure science. So they're models for natural agents. If you want to learn something about nature, since there are limits to what we can do with natural agents, we are allowed by some ethical committees to do horrible things to animals. It turns out that you can't do some of these things to undergraduates anymore. I still am shocked by this. So if you're going to try to dissect somebody's brain to find out how they work, and you're not allowed to anymore, you might as well try to, instead of an analytic approach that takes things apart, you can try a synthetic approach that puts things together, so working bottom up, and robots allow you to do that very well. So the theme for this conference is the impact on our future from computer science, and of course for me it's from robotics. And I don't need to go into much detail about how much robotics is already impacting us and has been impacting us for some years. So industrial robots have been around for at least 30 or 40 years now. And Moshe already gave a wonderful talk yesterday that was exactly talking about the effects of such industrial robots and the automation that they bring. And we can debate whether these effects are more benign than less so. But that's the debate. The fact is that the robots are there. There are millions of consumer robots already in use. In Spain, I was mentioning this before, but one of the statistics mentioned that Spain is sort of an outlier, so it's 25% of the vacuum cleaners sold are robotic vacuum cleaners, but overall it's about 10%. Lawnmowers, pool cleaners, there are 2 Israeli companies who, in each of these territories, who control anywhere from 40 to 60% of the market. Window cleaners, all of these things are already there for consumers. Commercial service robotics, the clean walkways and do security patrols. I need to plug in my own company, Blade Ranger, which is developing robots for cleaning solar panels. These are all things that are happening right now, and they're part of our present. We're not talking about future impact. There's, of course, the near future, and I think, for many years I've been working on robot teams, and here are some movies from my lab. And these have been transitioning slowly into industry. So I think they're impacting us in the near future, and some of them are already in present. So if you look at something like Kiva Systems, which was sold to Amazon and became Amazon Robotics, automating their warehouses, or this was actually a good point for a transition. This is a project that we did with a commercial company where the results of that project are already out there working, and I'm no longer privy to them. This is my pride and joy in some sense. This is the best Israeli soccer team in the history of the state. So made it to the top 16 3 times in a row worldwide in the World Cup. Unfortunately, this says something. So fortunately, it says something about the quality of our robotics. Unfortunately, it says something about the quality of our soccer. So I had a heckler once in one of the talks. He said, well, that's not a big achievement to have the... So it's true, but these are all robots in my lab, except for, of course, Amazon Robotics there. So these are things that are happening. These are teams. They talk to each other. They're completely distributed in the sense that each one has its own computer, has its own device. There's no central controller for these things. Kiva Systems is cheating a little bit. There's a hybrid system there, and I'll go into this in a little bit. But this is something that is happening now, and I'm having a problem transitioning. So there we go. Okay. So if this is going on so well, I mean, there's sort of this kind of vague understanding, intuition, I should say, that we all agree with, I think. Well, we have multiple robots. It's definitely cheaper, better in some sense, and certain for many applications than one. So why not just do it everywhere? So you can think of teams of autonomous cars, and you can think of delivery drones all over in the hundreds of thousands or so, and you can think about cleaning in teams and so forth to cover larger areas. And all of these applications indeed are possible, except that they're not that easy. So the scaling up part from the transitioning from what we're seeing today, which is up to a few hundred robots at best, to actually generating fleets, okay? Huge number of robots. It turns out that it's actually not very easy, and we can see it already in what has happened to Amazon. So Amazon started, or Kiva Systems started with a few hundred individual robots that would talk between themselves and agree on what needs to get done. It turns out that this didn't work very well, and they ended up with a hybrid controller. So there's a central server that actually, if you're a theoretical computer science, think of it as the K-server problem. It's actually assigning tasks to the robot. It tells them where to go and pick up things. The actual planning initially was done on the robots, then was also moved to the cloud or to the server. Okay? The collision avoidance is on the robot, and the reason for this is latency. You can't have the server actually detect collisions in time, and so for safety, it's very important. So this is an example of cheating, which I'm not, of course, I don't mean that in a negative sense. It's a commercial world that they need to sell something that works, and they do it very well. But I think it tells us something about where the limits are. Okay? And the limits is that there's something called, well, I call it the interaction bandwidth, for lack of a better word. But it's something in the bandwidth that allows robots to actually communicate, or computers to communicate between themselves. And by the way, interestingly enough, it's happening all the internet too. When the internet was first out, we started talking about distributed computing in the large. What ended up happening is that we have a lot of central servers, centralized services that are providing services to all. And it's true that we can still, some of the computation is still distributed. A lot of the services end up being centralized. It's easier, it's cheaper to manage. And so we ended up something that's less than distributed. So there's a limit here, which is inherent. If I'm standing here in the audience and one of you is taller than the other, then I won't be seeing past that person. I will not be able to actually be able to interact with that, with a member of the audience. If we're all sitting in an audience, if we're all sitting outside, the person right here at the front, Leroy, is not able to see what's going on behind him without offending me, of course. And he's a very polite person, he wouldn't do that. So the problem is that we're facing inherent limits to the interactions between them, so we can no longer talk about having this global coordination and overall planning, which is still distributed. I'm not talking about centralization, I'm just talking about the ability to globally coordinate. So this is leading to what I call swarmy systems. Okay, where you're losing some of the interactions, and so it does happen with scale, but normally when people talk about swarms, they talk about large-scale systems, but it's actually the cause, not the effect. So when you have a lot of agents, the limits becomes apparent, and therefore you are getting into swarms. It's not that, because it's not nothing to do with the number. It's got to do with the limits of the bandwidth that exists within the system. So you've got all these problems with physical occlusion, with communication regions, and so forth. And the result is that you've got these multiple clusters of coordination that are happening in parallel. Each one of them is completely local. You can't plan it or completely control it in advance, certainly, but even in real time, because it's happening in parallel over, there's no way to do this. And so we're moving from teams to swarm, and I think this is where the future of, at least of the science, lies, is in pushing that envelope when you're talking about multi-robot systems. Now, there's a lot of great interest scientifically. This has been known, and a lot of work has been going on swarms for many years. This is not a new thing. I have to say, I've been one of the people who avoided doing swarms for many years because I couldn't find where in reality I would use them. So, you know, I was coming up, I had this very applied notion where I wanted to work on a problem that would really affect the real world. And it's hard to find a problem where swarms in the near future are going to be needed. And the reason for this is exactly because companies are extremely good at cheating. So they provide the answers that we need, and they make do with centralization and with global bandwidth that allows everybody to communicate. But recently, in the last 2 or 3, well, maybe more, 5 years, I've had a change of heart, and I found myself finding two areas in which swarms actually are inherent and can have a very large impact. One of them is in medicine, having molecular robots inside the body, where there's just no way that a tiny robot here, made on a nanoscale size, can communicate with trillions of other nanobots that are distributed around the body. And the other one is in the models of biology. So it's true that I can build a group of robots that look like they're swarming without actually swarming in my lab, because Wi-Fi allows me to do that. But that's not a good model for what's happening. So the use of robots as models for biology and for what I would call animal psychology is also something that is inherently swarmy. Okay? So I'd like to talk very, very briefly about 2 high-risk, high-payoff preliminary, I would like to emphasize this, investigations that are taking place right now in the preliminary results. One of them is on medical molecular robots that I've started a few years ago. These are robots that are, well, these guys, when they're closed, about 35, this is about 35 nanometers, this is about 50 when they open up, so it's about no more than 100 nanometers. So they're overall the size of an influenza virus or slightly below. These guys are from DNA, they're not my work. They're made from Douglas et al., Mido Bachelet, and George Church at Harvard. But Ido was working at Bar Ilan, and he brought them with us and the knowledge, and we started interacting. And the idea was to try to see what we can do with these things. Now, the way these things work, if you notice, there are these two arms at the front. Okay, these are made from DNA strands, and when they hybridize, the gate opens. So this is a clamshell robot. It holds a drug inside, and intentionally, the original intent for this was to do targeted drug delivery. When the toe holds the two DNA strands hybridize with a cell or with another DNA segment, then the thing opens. So really what's going on here in the computer science terms, and this is the part where I think Ido found it useful to talk to a computer scientist, was that this is really an if-then rule. You've got an AND gate, you've got an if statement that can ask about two conditions, and if both conditions match, then it opens up, and therefore you've got a then part. Okay? Now, in computer science, we actually know these things, that we know that we can change this, and you will have trillions of these, so the problem of how many rules you have or how many repetitions of the rules you have goes away. And you actually can talk about now what I would call nanoswarms or nanococktails. Okay? Theoretically, these things look a little bit like population protocols from distributed computing, or they look like string rewriting systems, which is a model that is Turing equivalent, has not been used, I think, in many years, because everybody now just talks about Turing equivalence. But these are things that we can talk about on the theory part. My interest in this, however, is not the DNA computation. There's a fairly sizable and noticeable community that does DNA computation and will use these things to build circuits. That's not my interest. I'm not interested in injecting you with nanobots so they can compute pi. Okay? I'm trying to inject you with nanobots because I want to cure you of everything you might ever have. This is my best chance of providing myself and others with immortality. So the focus here is not a medical treatment. And there was an epiphany moment when I sat with Ido at a coffee house. It was very late at night. We were both frustrated. It was 2 years we started talking. Nothing is coming out from this. And suddenly he said, you can reduce all of medicine to two things: delivering good stuff and preventing bad stuff from being delivered. Those are the two things that you need your robots to do. And I said, okay, this I understand. Yeah, that's it. So if we can deliver good stuff to where we want it, and we can prevent bad stuff from arriving at where it should have gone, and want to prevent it, then we're doing medicine, and that's it. These are two tasks for robotics that I can understand. And so we started fiddling around with the idea of these swarm drugs. And there's an interesting thing here, and none of you, I think, here are people here from biology, but I think none of you here are from medicine. But the way medicine thinks about drugs is the way we would think about consumer devices or typewriters. That is, if you look at the history of engineering, it's always the same phenomenon. We start with very specialized devices, and in many cases, not all the time, we start generalizing from them. So if you think back to the 80s, those of you who have been around at the time, we had games. They were about smartphone size. They played one game. You wanted a different game, you would buy a different device. If I would come up to any one of my students and I tell them, look, I have this idea for a new game, a new type of Candy Crush, or Angry Birds. It will actually kill the market, Fortnite, whatever, right? Let's build a new phone for it. They would look at me like crazy. But this is the way medicine and drugs are being done. Each drug is specialized for the treatment it's supposed to give. If you're very lucky, it will solve cancer and you get a Nobel Prize, or it will solve baldness and you get very rich. But that wasn't the intent of why you built this drug. The drug is made to do damn thing. This allows you to suddenly start talking about reusable platforms. Because, and this is what the doctors don't understand, we can chain these things. Where as engineering, we understand about building circuits, and we can start chaining the nanobots together to create larger systems that are more complex and can respond to more and different conditions. The interesting thing about it, that this is a revolution in medicine, because now, well, there's this issue of reusability, which now allows you to spread the expertise, because now you have people who can build robots without thinking about the treatment, and you can think about people who are doing the treatment without worrying about the robots. And if this sounds familiar, that's exactly the software versus hardware abstractions that we like, and we have done so well in the technology side to use, right? So it speeds up the process. The other thing about it is that the FDA is actually much faster to approve combinations of known drugs rather than new complete drugs. So if you've got the platforms approved, then now all the list of drugs that you've ever heard about, I can put on this, and it'll be fast-tracked through the FDA. And so the time to take new drugs to the market that are actually combinations of things that we know about is entirely reduced, okay? So I actually don't want to talk so much about the medicine part. We've done our share of working about how do you program these things, built a compiler for this, and so forth. But I actually want to talk about a thought experiment that we did. And the idea was, because once we started talking about nanobots, people became very stressed about the safety of these things. And so I want to go back to Asimov's laws of robotics. Now, roboticists typically hate Asimov's laws of robotics and discussing them because they're literary fiction, very clever, ingenious, in fact, for the literature they caused and enable, but they have nothing to do with safety or robotics in the real world. However, there are significant philosophical advantages to thinking about them because it sort of explores the limits of what we can do. So even talking about safety and then showing that Asimov was not safe is a good exercise from a philosophical perspective. So Asimov, for those of you who don't know, I'll very briefly go through. They had invented this world where the three laws of robotics exist. The first law is that you can never harm a human. The second law is that you will always do a commanded unless it harms a human. The third law is that you will protect yourself unless it conflicts with the other two laws. And as I said, it's a philosophical device, but we're actually going to do it with nanobots now. So the idea is that we're actually going to build three types of nanobots. There's I will call it the L2 robots. They just have a task. This is the command. So they do whatever they're programmed to do. Okay? Cure cancer, solve Alzheimer, cure male baldness, whatever you want. Okay? The problem is that you want to stop them in case there is harm. So you introduce a new type of robot into the system, which is the L1 robot, which closes the clamshells. And very briefly, I'll show how this is done. Okay? If it detects harm. And the problem then becomes, how do you detect harm? Now, it turns out that you need actually a third type of robot, which is to maintain the ratio of the L1 and L2. Because it could be that the side effect of the L2s working is that they actually key in the L1s, and then there's nothing to stop them, and you have a system that escalates. So you actually do need these three types of robots, and you've got a population of swarm robots, nanobots in this case, that actually obeys the laws of Asimov, even though no one robot can actually follow this procedure of three laws, right? Because it can only do an if-then. And this is the way it's done. You start by introducing you have got the L2 robot, and then we can talk about the L1 robots. The L1 robots respond to intracellular materials. If they appear in the bloodstream, that means that actually cells are breaking apart. And it turns out that, in fact, some of our nerves in our own body respond to this and respond with pain. So this is part of the mechanisms that the body already has for detecting harm. Okay? In particular, we use the miR-16 molecule. And what happens is that when the miR-16 reaches or is detected by the L1s, they open up. What do they present? They present exactly the DNA strands that turn to close the L2s. They compete with the L2s over what it is that they do. So, and you can see it also in the microscopy here, right? You've got these are different L1s and L2s separately, and then they create these complexes when they're brought together. Now you need a third one, which is to maintain the balance between them. And we've played around empirically to try to find what the right balance is for the experiment that we were doing. And just to show you how these things work, so you start with an incorrect ratio. You've got these three types of robots. When everything is fine, then the third robot, the L3 robot, actually enables the other two to work. And just to do this, to complete the analogy all the way, we've taken the earliest story that Asimov introduced, which is Runaround, in which he introduced the three laws of robotics, and we've recreated it in nanoswarms. So I won't go into the story. How much time do I have now? Yeah, I'm not going to go into the story, but essentially he shows a very clever idea where all the laws work, and yet the robots gets into trouble because of equilibrium, and we've done it inside a testing tube, and you can show in the lab. And you can see, in fact, that the robots start working, they get into conflicts, so they equilibrize, and then you need to introduce the L1s or harm in order to break the equilibrium, which is exactly what is happening in the story. So this is both, I think, a testament to the genius of Asimov, that he was actually predicting correctly same certain phenomena. But the ability for us, the achievement here was to actually show that we can recreate the same thing first in a swarm environment. So none of the robots actually is aware of all the three laws. And two, I think it really does introduce issues of safety and shows that at least some notions of safety are possible even in medical nanorobotics world. So this is the first kind of inherent application and future impact of nanobots that I'm seeing, and I think this will take some years to do. So this is far future, but I think it has a lot of benefits. The other thing I want to talk about very briefly is the robots as model of nature. And again, this is an area I think with the potential for lots of impact. Of course, nature is filled, I would put the obligatory picture of birds flocking and fish eating each other and all that stuff, but you've all seen it, and everybody uses the same pictures too, so it becomes boring. But nature is just filled with swarms. It's actually interesting to the degree that nature is filled with swarms, but engineering is not. And I said that's because companies, and well, us too, are very good at cheating and overcoming the actual limitations of swarm. And we've been investigating swarms since the 60s. I'm talking about just robotics. But, so this is, again, in my lab. And what I'd like to do, and I've been doing for a little bit now, for a few years, is model insects, okay? Or at least, let's say, animals that we don't eat and we don't like as pets. Let me put it this way, okay? Now, the interesting thing about it is, of course, there's only local information, but we know of all swarm. There's another thing here, which is that you also get partial information. This is something where the robots brought into bear. Most of the models the theoretical models that exist to describe what swarms do, and these type of tasks, this is foraging, this is another type of foraging where you try to hit a food spot and bring it back. In most of them, the assumption is that when you collide with something, you know something about the other robot. So you know the action it took to avoid you. You know the direction it is facing. You know it is a robot. But this is actually not so easy to do in robotics. At best, we can measure distance. I can't tell the heading of the other robot. Okay? So there's very poor information that exists that I can play with when I work. And therefore, most of the theoretical models that exist, even though we can replicate many things empirically, the theoretical models that allow us to actually talk about what's going on are actually completely out of sync with what the reality of what these insects would do, and we see this in the robots too. Okay? So I want to just show you briefly what the life of a swarm robot looks like. Okay? It starts by acting on its own pre-programmed task. So we'll mark it as P. And this is the timeline here. So it starts here, and it starts doing whatever it was born to do, which I guess is to eat and breed. Okay? And then it gets too close to something, so he wants to avoid it, which we'll mark with A. And the time is being spent now on avoiding it, and hopefully he manages to either run away or avoid it, and so he gets back to doing P. And this will repeat, repeat, repeat until time runs out, and he dies or, in some fashion or another. Okay? So from the life of the swarm robot, or the swarm insect, this is what timeline looks like. I do my thing, I stop doing my thing. I do my thing, I stop doing my thing. Okay? So if you try to actually describe it in theoretical terms, this looks like an extensive form game. The story of life. Yeah. Yeah, it's actually a sad statement that we can... The fact that all of you have imagined yourself doing P&A here is saying something too. So extensive form games can describe this thing in principle, right? So we start doing a thing, and then we have a collision, okay? And the robots get into a first collision. Everybody in the system who gets into the collision now has to resolve it. And once it's resolved, they buy themselves some time until they get into a second collision, okay? And so forth and so forth and so on until time runs out. So what you do at the end, you sum up the reward that you got here at the end, and then you know whether this was a good path or not. And this is a game, that is, this describes a single lifetime of the system, the entire swarm, okay? Of course, this is very theoretical. This does not work. And the reason for there are many reasons why it doesn't work, but here's one reason it doesn't work. The swarm robots can't actually choose based on gains and costs. They have no access to the gains of costs. They don't know their own. I refuse to believe insects can value their own actions, okay? I think even people have a problem understanding, how much money are they making right now by sitting here or not sitting here, which is a choice, okay? So the swarm robots don't know the utility. They certainly don't know the global utility. So they don't know what others are making. The only thing they can measure is time. And what we're doing is looking at how much time they're spending actually doing their thing versus how much time they're avoiding each other. And if you look at that, that's called the coordination overhead. And it's simply percentage of the overall time being spent by everybody avoiding, okay? Versus the entire time being spent just doing everything, the avoiding and the program. The larger this is, the worse. Because the system is now in overhead coordinating instead of actually doing what the system was supposed to be doing. Now, under certain assumptions, you can actually show that to maximize this, you actually need to only minimize that. So that gives you now, turns into a game, into a potential game, because now you know that you can decrease the time, no matter what the gains and the utilities are actually, if you're measuring them in bits of food or in energy or in whatever you want, it doesn't matter. You can just reduce the time you're spending on coordination. And again, we're talking about the bandwidth. So if you do that, then you're fine. The problem is this is, of course, still global. So we want to move away from that. And it also requires you to make predictions ahead. Because, again, we're talking about extensive foreign, so I'm having to choose the path that's true for the entire lifetime of the swarm. How can a single insect or a single swarm member predict ahead what the right actions will be? So first of all, we get rid of the time by making an assumption that all the collisions have the same effect. That is, if I collide with you and I spend some time on this, the next time I collide with somebody, I will spend the exact same time. And this then becomes, I can compress the entire tree of the extensive form game into a series of matrix game. Each one of them is identical. And then I can make another assumption, or I can show another thing, which is to look at there's a slight difference between this and marginal utility, but let's call it the marginal utility of, from my own perspective, my contribution to the system. In papers in Agents, it began as something called the Wonderful Life Utility, referring to the movie where this person is being shown the value of his life and what would the value of his life be for others without him. Okay, so you can actually look at this. This is the value. This is the WLU, my estimation, okay, of how much I'm contributing or not contributing to the system. This is my overhead. I'm agent I here. So this part is easy to understand. There's another factor that goes in, which is the effect on others. And this becomes a very interesting point because, of course, I can't really know the effect of others, but now I can engage in several different complexities as to how much I want to invest in actually approximating what others do. So, for example, I can do what people at least do with mirror neurons, and I can assume that others are like me. And so if I've been affected in the past, I can learn from that and assume that you're going to be affected in the same way. I can take worst case scenarios and say, I've been affected very badly in the past, so I'll assume the same for you, and so forth and so forth. But this is now where the game is, because the first part, this part is known. I can measure this. This is my clocks, so I can measure this with no problem. This part is where I have to estimate, and the better I do estimation this, the better I am to the reward. And the interesting thing about this, of course, is that if I use this particular reward, if I use this particular payoff, I'm aligned with everybody else. So I'm guaranteed to actually play the Nash equilibrium. Okay? Now, the results of this, and we've published a few papers talking about different approximations while developing the story. And the results of this is that you can actually use now very simple reinforcement learning algorithms, nothing fancy, with what I've shown you as the formula as the reward structure. So it's a simple payoff, and you just fit it into the reinforcement learning algorithm, and magically the robots begin to coordinate better, and in fact they improve k-fold over what they were doing before, even with sometimes, we tested this is not shown here, but we tested this with the Kiva Systems Simulator. They published very early on when they formed the companies, they published something called the Alphabet Soup, which is a simulation of their system. And the idea, they were trying to promote people to actually play around with the K-server tasks, right, with the assignment. And they gave a very quick implementation of how the collision avoidance worked, which showed we can improve what they were doing by sometimes by up to 3 times, just by playing with the local collisions, letting the system learn how to collide better. Okay.
What do they try to accomplish?
Okay, sorry. So just because of time, I was saying it. So here, this is a foraging. So they're collecting soda cans and bidding them to the blue. Okay. This is a variant of this. This is search. In both cases, they don't know where they are. They can't communicate. They're just going out there individually and doing their own. But they're getting measured on how many soda cans they brought over. Okay. This is a variant on this here. The soda cans are actually fixed. They have to bump into them in order to show that they've won, and then they have to report back. Okay. Now, just very briefly, okay, this is a complex graph I'm not showing, so I'm just going to give you the highlights, okay, which is we are good, the other ones are worse. Let's do this. Okay, so what you're seeing here, this is actually measuring the mix of different techniques that you could try to do to avoid collisions. And this, the y-axis, is measuring how well you did overall in the system after letting it learn. There are different variants of our model all show up at the top. This is when you don't do learning, so everybody's homogeneous, and you show that, in fact, they're not doing as well. And this is previous work that does not guarantee convergence. So, in fact, sometimes they do well, sometimes not, but ours are actually guaranteed to converge. Okay? And I can show you also, this is surprising, but we are actually even beating if you give access to the system about the global utility, so you let the robots cheat and you tell them how much they're actually pucks or food they're bringing in, we're still beating them. Okay? Now, I'll just do a small plugin. We just recently started the Swartz Smart Center. We just finished our first year, funded by the ISF. Thank you very much, Joe. And these are 4 groups. I'm leading the group, the center, but it's my group, Noah Agmon's group at the Bar-Ilan, Freddie Brookstein's group at Technion. And at Tel Aviv, we have a biologist, Amir Ayali, who studies locusts. And the idea for the center is to actually study computer science and biology questions enabled by mixing together robots and locusts in the same environment. So we're actually trying to build small robots that can act as locust nymphs, so they walk, they don't fly. And in Amir Ayali's lab, you can see movies of these things going around. It turns out that locusts are very interesting from a swarm perspective. They're almost pure swarms when they're in their swarming state, and they're pure individuals when they're in individual state. They actually switch between them. So it's not that locusts, you put them together and they immediately start tearing everything apart. So my goal, and I think we're getting close to it, but my goal would be to show that these insects are rational, which is an interesting, cool thing given that humans are not. Okay? So if you could show that a hive mind, in fact, or at least the hive of the locust here, is in fact rational, I think this is an interesting scientific result. What? You tried elections? I think that's one of the proofs that. Okay. So just to very quickly summarize, obviously multiple robots are better than one in some cases. That's not the interesting point. Here's the interesting point. The interesting point is that the future impact of multiple robots is actually not so much in the building of the robots. It's in solving the interaction bandwidth between them. And we can cheat only for so long. And in many applications, that's going to be enough. But there's some applications, and there's certainly some areas of impact for science where you can't cheat. Medicine being the application and models for biology being the model for science. And you have to be able to understand how to resolve this in completely swarmy ways. And I've shown you some preliminary results, and of course I would love to take your questions. Thank you.
Swarms in nature or just populations of animals, it's hard not to think about the dynamics from evolution and genetics.
Yes.
So do you think that evolutionary algorithms will make a comeback when studying swarms in the future, or do you think it won't?
So it's not that they have to come back, they're already there. The problem, I'm giving you my bias, okay? I'm not interested in engineering these things. I'm interested in understanding these things. The problem I have with evolutionary computation is very often the same problem I have with deep networks, which is that they do this wonderful thing, and which frustrates me even more, because now I have more that I don't understand. Okay? So if I were, for example, a machine vision person right now, I would be completely excited by the enablement that deep learning brings to building machine vision systems, and be completely frustrated by the fact that up until now I had the human brain and the animal brain to compare against and say, this is a black box I don't understand. Now I also have a synthetic black box I don't understand. So it's even more frustrating. The evolutionists are there, they're playing. The learning that I've showed you is not on the evolutionary stage. So this is within very much the lifetime of the system. What I would think happens is that some of the things would stick around for the next generation. And I think that becomes very interesting. But then it really becomes much more interesting when we introduce prey and predators into the system, because then there's a context to the evolution in terms of survival. I can hear you fine.
Okay. So my question is about the cheating part that you say. Why not cheating? Because it seems like Amazon maybe in some way got it right, that assuming a central controller for most or maybe part of the task while playing for other tasks individually seems to be the right approach. Maybe, I don't know, for modeling, but for medical, it seems to be a good approach.
Okay, so First of all, on the commercial or application side, if you have if you have a way to cure cancer while cheating on the interaction, on the bandwidth, by all means, please do that. Okay? Personally, also male baldness also somewhere ranks in there, but that's a personal bias. So that's not, I'm not arguing against cheating when it is possible, certainly when you want to get something applied. My argument was actually different. My argument was that in some cases, let's talk about the application side, you can't cheat. So even in medical nanorobots, the closest you can come to cheating is applying magnetisms or magnets or electrical fields or light from the outside, which will become as a sort of an attractor, okay? And we can do that, so you can apply magnets at certain areas to make sure that more nanobots get to the area. Still, it doesn't control the interactions between them. So that might be a way to sort of hybridize the system. It'll attract more nanorobots to the area, but still the interactions between them have to be local, okay? Most of the applications, however, so light, for example, you can only go through the skin by some depthness, so you can't really use that. Magnets, you have to, if you want to put them in, you have to insert. So overall, I think medicine, at least molecular nanorobots for medicine, are actually a great example of an application where you can't rely on cheating through hybrid methods.
Doesn't the body already have swarming drugs in the form of the immune cells, the T cells, the neutrophils, the eosinophils, and others?
Yeah.
So if you put into the body robot swarming drugs, so to speak, would they conflict? Would they abet one another?
Okay, so let me start by saying I'm not a biologist, I'm not a medical doctor. I work with those. And so everything I say, I am, if I fail at that, it's of course my misunderstanding of the state of the art. But here's what I know. So first of all, you're right, and we're introducing foreign bodies into the body, and it might respond, and in some cases it does. Gold nanoparticles can live for months without affecting the system. In fact, their main use right now medically, or at least in the labs, it's not for these type of things. They don't do swarms. They let the gold particles accumulate where the cancer cells are. So they're used for imaging. But that's a great example of something that can live in the body and the body doesn't harm it because of the gold. The DNA origami robots that Ido did, he did a demonstration. He has a paper later on, which I was not involved in, it's all his work and his group, which he called it a computer inside a living animal. And he actually demonstrated that the DNA can survive in cockroaches for about 26 hours. Now, I have two problems with them. So that's the positive outlook on this. My own take on this is that this is a failure in two senses. First of all, I refuse to call cockroaches animals. And two, the experiment from my perspective failed because the cockroach lived for 26 hours. It should have died much sooner. But yes, they are there. The problem of macrophages and others expelling those things is an issue, but it turns out that for at least a few hours, you're okay. The real problem you should be worried about, and we should all be worried about, is once the whole idea behind these DNA origami clamshells is to protect very toxic drugs from reaching your system. Now, we're talking about these robots are measured, their time length or their duration in the body is measured in half time. That means that at some point these things break apart and then they start releasing toxins, not where they're supposed to do this, okay? On the other hand, the accumulation of the number of toxins they bring to bear is just so minuscule compared to what we're being fed through chemotherapy and other methods that it's entirely a completely different level of risk, much lower.
We need to move on. Thank you very much.
Thank you.